Welcome to this presentation on discrete time sinusoidal signal. This is a very important topic. We will use the results of this presentation repeatedly throughout this week. We will discuss continuous time sinusoidal signals, what happens when they get discretized. We will discuss the concepts of uniqueness and alias. Let us consider a continuous time sinusoidal signal of this form. I have A to indicate that it is analog. This A is amplitude, omega is frequency in radians per second, theta is phase in radians, time t is in seconds, time goes from minus infinity to plus infinity. Let us define this capital F frequency in cycles per second or hertz, defined as omega equals 2 pi f. We get this expression for ua of t, where I have replaced omega by 2 pi f. We will show that Tp given below is the period. Tp is given as 1 over f. The variables here A, omega and f are in capitals. You have to remember this. We use capitals when we deal with analog signals in this presentation. Let us consider the sinusoidal signal shown in the previous slide. Let us fix f. We want to show that it is periodic with period Tp given as 1 over f, where f is the frequency. So let us evaluate ua of t plus Tp. So come to this expression. In the place of t, I will put t plus Tp. So let me put Tp, and Tp is 1 over f. So I write 1 over f plus this theta, close it. Let us multiply this out. So I get 2 pi here, f and f cancel each other. So 2 pi, I write it first, and then 2 pi ft plus theta. Now this is cos of 2 pi plus something. So we get cos of that something. So we get a cos of 2 pi ft plus theta, and notice that this is nothing but ua of t, and hence we say that this signal is periodic with period Tp given as 1 over f. It is obvious that continuous signals with different frequencies are different, but we will illustrate it with an example. Let us say that u1 is given by this sinusoid cosine function, u2 is 7 times faster than this, 7 times higher frequency. You have 7 here. So you can see the slow changing signal, and this is the fast changing signal. It is easy for us to see that these two waveforms are different. We can increase f all the way to infinity or decrease all the way to 0. Even with a very small change, you will see that you get a completely different waveform. But we will see that the situation changes when we go to discrete time signals. To start with, let us define a discrete time signal un as this. Recall that this symbol denotes defined by n is a sampling number, it goes from minus infinity to plus infinity, it is an integer, and omega is 2 pi f. Note that I am using small letters here to indicate discrete time signals. So omega is radian frequency, it is given by 2 pi f. Now I am going to substitute in the place of omega 2 pi f plus n times n plus theta. I have written it as in red because you will need to recall it in a subsequent slide. You may even want to write this down. So n, as I said earlier, is an integer variable or sample number. A is the amplitude of the sinusoid. Omega is the frequency in radians per sample. So that when I multiply this by sample number, it becomes frequency in radians. theta is phase in radians, f will be called the normalized frequency with units of cycles per sample. We will see the reason for this name shortly. In discrete time signals, we have this equality. On the left hand side you have added 2 pi n, and because of the trigonometric property of cosine signals, whenever I add this 2 pi n, I get this back. So all sinusoids of the form ukn a cos omega k n plus theta, where omega k is given as omega 0 plus 2 k pi, k is an integer, and pi goes from minus pi to pi, are indistinguishable or identical. We also say that omega k and omega 0 are separated by integer multiples of 2 pi. So we say that sinusoids in minus pi to pi only are different. If omega equals 2 pi f, then in the place of omega 0 I get f0 by dividing throughout by 2 pi. So I get minus half here and plus half here. So for this f naught in the range minus half to half only, we get unique sinusoids. If you go outside, they are not at all identical. Now let us sample a continuous time signal. This is the important requirement in this course. We deal with discrete time signals in this course. Let us suppose that we have the analog signal that we encountered earlier. Let us sample it at a sampling period of Ts seconds, or frequency Fs in samples per second. So T is given as n times Ts. So we start the sampling at t equals 0. So you get nTs at time t, and in the place of Ts we have to put 1 over Fs. This is the sampling frequency, this is the sampling period. So let us substitute it here. In the place of t we put nTs, and as per our convention we write only n. This is ua evaluated at nTs, and n goes from minus infinity to plus infinity. So let us substitute for t from here. T is nTs. So let us write a cos 2 pi f. In the place of t we write nTs, I write tsn plus theta. Now let us write as a cos 2 pi. In the place of Ts I will put 1 over Fs. So I had 2 pi, Fts I write f by Fs times n plus theta, and recall our earlier definition of un. Recall what was written in red earlier in a previous slide, which I asked you to write down. It was nothing but this. Comparing these two, we see that f is equal to f by Fs. So we call it as scaled frequency, okay, f divided by Fs. So we had f equals f by Fs, small f equals capital F by capital Fs. Recall that we are using uppercase symbols like this for continuous time signals, small letters for discrete time signals. Of course, we have been using throughout the sampling frequency as capital F of s. The unit of f is, capital F is cycles per second. Unit of the sampling frequency is number of samples per second. So in fact you can see that this second and second will cancel. You get the unit of small f as cycles per samples. We will come back to this. We will multiply both sides by 2 pi. We get 2 pi f, which is small omega, 2 pi capital F, we get capital omega, and this is nothing but omega times Ts, because we know that sampling frequency is the reciprocal of sampling period. Because of this ratio, we call f as normalized frequency, and the units are cycles per sample. let us apply the uniqueness condition for sample signal. Remember, we had unique signals only in a 2 pi range for omega. So as a result, we can write it as minus pi to pi. This also corresponds to a period of 2 pi. So when I divide throughout by 2 pi, I get f as minus half to plus half. So when I have half here, that is the largest value, this becomes f max. F max becomes half into fs from here, or fs by 2. When I multiply both sides by 2 pi, I get capital omega max equals 2 pi capital F max, and because maximum value of this is Fs by 2, if I substitute, becomes pi Fs or pi by Ts. This is an important property. We will make use of this in subsequent lectures. We will now study some properties of discrete time sinusoids. We will take up the important concept of alias. We saw that when omega 0 increases, frequency of oscillation increases, it reaches a maximum at omega 0 equals pi. What happens when omega 0 is greater than pi? So let us take omega 1 equals omega 0 and let omega 2 be equal to 2 pi minus omega. So you see that omega 2 is greater than pi. Let us take u1 of n equals a cos omega 1 n, and omega 1 equals omega 0, and u2 of n is a cos omega 2 n. So let us substitute. Omega 2 is 2 pi minus omega 0 times n. Now cos of 2 pi minus omega 0 will give omega 0. Of course, cos of 2 pi n minus something will also give that something. So I get a cos omega 0 n, and this is nothing but u1 of n. So we say that omega 2 is an alias of omega 1. So let us take our continuous time example we studied earlier. Remember, we studied two frequencies, one of them 7 times faster than the other one. We called them u1 and u2, sampling time of 1 second. So let us sample it. So this t becomes nts and ts is 1. I just have to write n here. So that is u2 of n, and I can write this as cos 2 pi into 7 by 8 into n. 7 by 8 I will write as 1 minus 1 by 8. So let us multiply now by 2 pi. I get 2 pi minus 2 pi by 8. So this is cos 2 pi minus something. So I get that something here, cos of 2 pi by 8 into n, and this is nothing but what I will get if I sample u1 of t at the same sampling speed. So this is u1 of n. So here is u1 of t, which is a slow waveform which is sampled at unit sampling intervals, whereas the faster moving one is given by u2 of t. When I sample them, I get this. Let me blow it up in the next slide. You can see that this is continuous waveform is u1 of t, slowly changing. This is a faster changing waveform which is u2 of t. When I sample, algebraically I showed that they are equal. You can see that when I sample with a sampling period of 1 second, so I sample it here, 0 here, I sample it here, I get this point at 2, at 3, at 4 and so on. You see that these two curves intersect exactly at these sampling instants. So we saw this equality algebraically in the previous slide. In this slide we see them through this figure. you can see that these two are identical. In fact, we can say that these two waveforms will be identical at all sampling instants, not only for the time duration shown here, but entire period from minus infinity to plus infinity, which we showed in the previous slide using an algebraic expression. We see that the faster signal is 7 times faster. It is easy to see. You can see 1, 2, 3 and half here, 3 and a half in the place of half waveform here. So it is 7 times faster, it is easy to see. While the continuous curves are different, they are identical at all sampling instants. This is caused by sampling. With this, we have come to the end of this presentation. Thanks for joining. Goodbye.